So let's take a look at these orthogonal projections in section 6.3. I want to help you give a kind of intuitive feel with this first example. And the question is, can you project this vector in R3 onto the span of these other two? What's nice about these two vectors in R3 is that we can actually graph them on the XY plane because the last entry is 0. So 5, 2, 0 stays on the paper. Negative 2, 5, 0 stays on the paper. Had those been other values, we would have moved up off the page or down into my desk. So that didn't happen. So think about what this question is asking is I now want to project this vector onto the span of these two. So think about what the span of these two vectors is everything in R2. Since we're going to come up with all the linear combinations, you'll never get off of the paper because the last two entries are both 0. So the span of these two vectors, since they are independent, is essentially the XY plane. So picture where this one is. If you were to go over 6, up 4, and then down 5. So currently I have a vector sitting right here, and then its last move is 5 units down through my desk. And what we want to do is, once it's down there, where we want to project it back up onto my sheet of paper. And where that lands is what we're trying to find. So this is what we call y hat. And y hat is just a series of projections of y onto each of these separate vectors. So remember that the general move is to dot the y vector on to the first one, which I'll call u1, over u dotted with itself. And so that's what we're going to do a few times. Now that just becomes a scalar. So, and then we're going to scale this vector. And we're going to do that a second time and add them all together. So I just want you to see that's the generic move we're going for here. So let me point and get these up here. So again, I'm dot product of y versus the first vector. 6 times 5, 4 times 2, and negative 5 times 0. Over u dotted with itself. So 5 times 5 plus 2 times 2 plus 0 times 0. So that's going to become the scalar in front of the u vector. And then we do that one more time. So we've got y dotted with u2. So negative 12 plus 20 plus 0 over 4, 25 plus 0. And again, that's the scalar in front of this vector. So if we clean that up a bit, that ends up being 38/29 times that guy, and then 8/29 times the second one. Now those are some pretty nutty fractions, but believe it or not, I think it cleans up pretty nice. If you scale, for instance, 38/29 times 5, keep that number, and then you do 8/29 times negative 2, it actually turns out to be a pretty pleasant result. You can check it against your own calculations, but I believe this linear combination ends up being 6, 4, 0. So there's the answer, and we can be done and walk away, but I want us to think about, well, what does that mean? So think about what we're talking about over here. Remember this vector right here, over 6, up 4, and then down 5. If it were be projected back up onto my sheet of paper, notice the last move we did was as we went over 6 and up 4, we went down 5. Well, all we're doing is projecting it straight back up onto my sheet of paper, and where do you think that lands? At 6, 4, right there. And so that's not a surprise. That's where my projection ends up happening. Now there's one other part to this. So that's it. I've answered the question. We just projected that vector in R3 onto the span or the plane created by these two vectors, and it ends up right here. Well, there's often a second part to this. Well, what would that vector be that projects it straight back up to that sheet of paper? Well, all it was after we went 6 over 4, we went down 5. So it looks like it would just be a vector that shoots it back up 5 units. So let's figure out what that is. This, again, is what we call y bar. That's where we project it onto that span. This second piece, which I call the z vector, is just the original y minus the projection. So for us, that would be 6, 4, negative 5 minus 6, 4, 0. And that gives me 0, 0, negative 5. And what that gives me is another way to represent my original vector y. 6, 4, negative 5 as the sum of two orthogonal vectors. So my y bar is my y hat vector that we found here, 6, 4, 0, added to this z vector, 0, 0, negative 5. So sometimes we're asked to do that. And so what this is the sum of two orthogonal vectors. How do I know they're orthogonal? Their dot product is clearly 0. So let's look at a second example. This one is very difficult to imagine or to draw it out. We're in R4, so we just have to move to technique. So we're going to, and again, what this is asking ultimately is let's express this vector as the sum of two orthogonal vectors. And so this is being projected onto the span of these three. Again, I can't even tell you what this looks like. We're in R4, so we can kind of imagine this as a hyperplane through the origin in some four-dimensional space. And we're just projecting this onto that plane. So we're going to do the same thing. The move is exactly the same as what we did before. We're gonna dot y with each of those separate vectors, creating scalars for each one of those. So doing that, let's I'll do the first one and then we'll speed things up. So I'm just going to point this time and call out numbers. So 2 times 1, 2. 6 times 1 is 6. So 2 plus 6 so far is 8. 6 times 0, so I'm still at 8. And then negative 1 times 1, 8 minus 1, we're at 7. So that's 7. And then u dotted with itself, 1 squared plus 1 squared plus 0 squared plus 1 squared is 3. And so that becomes the scalar of 1, 1, 0, 1. So I'll speed this up. So if I dot y with u2, we end up getting the scalar 11 sixths times u2. And then finally, y dotted with u3, we'd end up with 3 over 3. So here's my linear combination. What we get, let's scale and add. Turns out this just ends up giving us negative 1/2, 6, 1, and 3/2. So that's one of my two-part answer. So I need to find another vector that's orthogonal to this that just becomes a sum, which gives me my original vector. And that's what we call the z vector. And we start with my original, 2, 6, 6, negative 1. We'll subtract my y hat. And that gives us that final 5 halves, 0, 5, negative 5 halves. So armed with those two, we can make a final statement that y hat 2, 6, 6, negative 1 can be shown as the sum of two orthogonal vectors. Y hat added to my z vector.